What do all these events have in common? They all involve things that move, and they all use force. People seem to enjoy moving things. If an object is standing still, someone will eventually want to pull on it, or push on it, change its direction, change its shape, or move it somewhere else. None of this would be possible without force. Force is simply a pull. Or it could be a push. Or a push that causes something to move. If an object is already moving, force can cause it to stop or change its motion. Suppose you don't like the shape of an object. Force can be used to change it into some other form. Controlling force has enabled us to literally move mountains and develop very complex ways of moving ourselves. Force is called a prime mover because it causes motion. There are other influences that are not force, but they are still prime movers because they act like force and cause some kind of motion. For example, liquids are forced or pushed through tubes by pressure. Without pressure, water would not flow from the tower through the pipes into the taps. Heat is moved from warm areas to cold, a motion which is caused by temperature difference. This is why we wear heavy clothing in the winter. It's to prevent the warm air next to our bodies from moving towards the cold air outside. We've learned to put the power of electricity to work, but without voltage, we would be unable to move electrons through the wires and the complex circuits, including those that are showing you this program. The pressure that moves fluids, the temperature difference that moves heat, and the voltage that causes electricity to flow are all prime movers. They all act like force because they cause motion. A prime mover, such as force, pressure, or voltage, usually acts as a system. Sometimes there are subsystems working within the system. A good example of many systems working together is the car. The mechanical system uses force to keep the 14,000-odd parts moving. The electrical system uses voltage to move electricity through the ignition and the accessories. Pressure in the fluid system moves things like brake fluid, antifreeze, and gas. The thermal system uses temperature difference to move heat away from the engine. Leonard is a mechanic who identifies these four systems when he's troubleshooting.
Okay, this car has an obvious problem that is missing. Now, what we need to do is we need to find out exactly what the problems are. Now, the problem could be either in the cooling system, it could be in the charging system, or it could be in the thermal system, but we're going to have to break it down in order to find out exactly what's wrong. What we'll do, we got the car hooked up to our scope. We'll check our RPMs, we'll check our vacuum, and we'll check our amp meters and see exactly what the problems are. Number one, we're going to take a look at the pattern. We'll raise the pattern up so we can identify. If we look at our pattern, we can see some inconsistencies in the height of our pattern, so that's telling us a particular problem that we're looking for. It's telling us a couple of things, that either we got not enough voltage going to the secondary system, or we got too much voltage going to the secondary system. In order to find that, we can identify it here on the scope. If we look at our pattern, we look at that spark line just running across, it indicates that number 1843, number 3, has a direct problem to it. And what it's telling us is that the spark plug gap is too wide. What we'll have to do is to remove the spark plug and re-gap the spark plug gap to ensure that it gets the proper clearance. After we have replaced the spark plugs and these kind of things, and it didn't work, then we're going to have to go on to further things. We're going to have to take a compression check to find out if there's any mechanical problems within. We might even have to go to the fuel system to try and see if the injectors are clogged up, whether we might have to blow them out or whatever. What we really need to do is be able to do a complete diagnosis and find out the particular problems this car and bring it back to factory specifications.
This is a common practice among technicians who deal with complicated systems. They break them down into mechanical, thermal, electrical, and fluid subsystems. By looking at systems separately, problems become easier to identify. Technology sometimes seems complicated and difficult to understand. But when the technology is broken down into its basic systems, and the forces or prime movers are identified, it not only becomes easier to understand the machines, it helps us build better ones for the future. Pulling, whether it's a little or a lot, takes force. When 15,000 tons of cargo have to be moved in less than a day, it takes a lot of force. These containers weigh up to 40 tons each, yet this crane is able to stack them on the deck of a ship as delicately as eggs in a carton. The crane is actually a combination of two systems. An electrical system provides power for the winches, while the cables, pulleys, and entire steel structure use force in a mechanical system. A mechanical system uses the force exerted by one object, pushing or pulling on another object, causing it to move or change shape. Wheels, gears, pulleys, and levers allow more force to push things farther, faster, or higher. Tom Jenner is a technician who spends his time in the powerhouse of this ship container crane. In order to maintain the lifting equipment, he must know about all the forces involved in the system and where they are applied.
This crane has the ability to lift 40 ton. It basically has two systems, an electrical system and a mechanical system. The electrical system consists of electric motor and the controls related to it. The electrical system is coupled to the mechanical system, and the mechanical system consists of the winch through the gearing, which plays out the cable and also pulls in the cable, which actually lifts the container. We have to place some restrictions on this equipment so we don't damage it. The limit that we place on it is an electronic limit on the electrical system. We limit the amount of force that we can develop through our regulator. When we lift the container, we have a force that we have to overcome, which is the weight of the container, which is 40 ton plus whatever force it takes to overcome the gravity. We lift the container up. Then the operator trolleys out, moves the container out over the ship. Once again, we have to overcome a force. This force is a smaller force. He trolleys out over the ship, spots the container where he wants to lower it. He lowers the container. Then we have another force that takes over in that we start to regenerate and go into dynamic braking. The net result is that all these forces add up and the container is put on the ship. As an electrician who maintains the equipment on the crane, I have to understand force and the pulling of the force so I can set up the parameters to limit the amount of pull that the crane can exert.
The net result, or net force, is what's left over when all the forces are added together. No matter how many forces are involved in this crane, there is only one net force, and it determines which way the container will move. In fact, when the operator controls the crane, what he's really controlling is the net force. Forces can be added or subtracted from each other like dollars, depending on which way they're acting. When forces act in the same direction, they add together to make a total, the net force. When they act in the opposite direction, they subtract from each other, and the net force is whatever's left over. These arrows you've been watching are called vectors. They point in the direction of the force. The longer the vector arrow, the greater the amount of force. Can you calculate the net force and predict which team will win this tug of war? The left team can pull 350 pounds. The right can pull 300 pounds. If you guessed the team on the left, you were correct, because there was a net force of 50 pounds to the left. If both teams had pulled with the same force, the net force would be 0, and no one would win. Net force applies to a tug of war in the same way it does to the crane and any other machine that uses a mechanical system. When the net force is 0, the system is balanced and nothing changes. When the system is unbalanced, the change is in the direction of the net force. Workers using a mechanical system must identify where the forces are acting, add them together to find the net force, and determine whether the system is balanced or unbalanced. Only then will it be possible to predict where the system will go and how much force is required to move it. probably opened lots of bottles, but have you ever wondered how they get the liquids in there in the first place? This machine fills 90 bottles a minute. It uses force in a complicated mechanical system to move the bottles around, but the job of getting the drink into the containers is done by applying force in a fluid system. Fluid systems are very important in our lives. Place these two fingers on your wrist and feel the fluids being pumped through your body right now. Blood is moving through your veins because your heart creates pressure. Pressure acts like force to move fluids through a system. A fluid can be either a liquid or a gas. When liquids are moved, it's called a hydraulic system, and when gases are moved, it's called a pneumatic system. In each case, pressure is the force-like quantity that moves the fluids from one place to another. Pressure also determines how much force a fluid exerts on a solid object, such as the air pressure pushing on the plunger in this tire pressure gauge. For technicians like Bob Burnham, who operates a fluid system, the job could not be done without pressure.
Bottling of soft drinks, we work with two systems: gas, which is CO2, and liquid. By introducing the liquid into the gas, we get the fizz, or what we call CO2 volume. Okay, my job is to maintain and check the CO2 volume to make sure it's at the proper levels at all times. What I'm doing here is checking the CO2 volume in the product. We take this instrument and puncture the top of the bottle, so we will get, when we shake the bottle, we will get CO2 pressure build up, and that will give us the amount of pressure in this bottle. As we puncture it, and we'll shake it up. That is going to bring up the amount of CO2 in the product. Now, CO2 volume is a result of pressure and temperature. Here we have 40 pounds of CO2 pressure in the bottle. Next, we take the temperature, and the combination of the pressure in the bottle and the temperature will give us the CO2 volume that we're after. If the CO2 volume is not in the proper standard, I have to adjust that at the carbocooler. The carbocooler pressure is what determines all of the CO2 volume. The carbocooler pressure runs higher than our bottle filler pressure, and that is what pushes our product into the bottle filler. It's very important for me in my job to understand how pressure moves liquid as a force to a lower pressure. It's like an electrician would have to know how voltage moves a charge. And if we don't know that, I cannot properly do my job, because pressure differential is probably the main ingredient in us producing our product. And if we don't understand that very well, it causes a lot of problems.
Bob Burnham knows that fluids move from areas of high pressure to low, and that the force moving the fluid is determined by pressure. Naturally, more pressure means more force, but sometimes there's a limit to the amount of pressure available. For example, the pump on this hydraulic jack creates pressure on the oil inside. As the pressure increases, the oil pushes against a piston and creates the lifting force. To calculate that force, the pressure is multiplied by the cross-sectional area of the piston. So the force is pressure times area. By changing either the pressure or the area, you change the lifting force of the jack. When the handle of the jack is pumped, what's happening is that the pressure is being increased, so the force is being increased. As the pressure increases, so does the lifting force of the jack. But soon a limit is reached where the jack cannot handle any more pressure. But the force can still be increased without increasing the pressure. Since force depends both on pressure and area, when you can't add more pressure, increase the area. That means you have to get a bigger jack. This jack has a piston with a larger area. So with the same amount of pressure as the smaller jack, it can produce more lifting force. It's this relationship between pressure, area, and force that technicians who work in fluid systems understand to control where the fluids will go. They know that changing either the pressure or the area changes the force. So, when you need a lot of force, how many devices can you think of that use electricity? Our computerized, automated world would quickly come to a halt without it. The flow of electrical charge through the countless wires and complicated circuits would not be possible without voltage, the prime mover in electrical systems. Voltage causes electricity to flow through wires. That is, of course, unless it's cut off at the source. The flow is very similar to the way water would stop flowing through a hose if its source was cut off. An electrical system is usually a circuit. The charge comes from a source. Then voltage moves it along a conductor, which carries it to a device that uses the electricity, like a toaster, for example. Then the conductor carries the charge back to the source to complete the circuit. Some circuits are only made of 2 wires, but for technicians like Terry Robertson, a circuit can be very complicated.
This is the 3585 spectrum analyzer. It is a complex electronic measuring device used to measure the different components in frequencies. It has 53 printed circuit boards with a multiple number of circuits upon each board, and it's very complex to troubleshoot. My job as a technician is to troubleshoot and calibrate this instrument up to customer specifications. In doing so, we use the voltmeter and also a block diagram and a schematic. In an instrument this complex, we break it down into block diagrams to determine which section our trouble is in. In this particular instrument, we have found that it's in the video filter, the A15 board. This is the schematic for the video filter. We see that we should have 5 volts on test point 1, and by following the path through, we come to test point 3, test point 4, test point 5. All of these should have 5 volts for the correct signal. Test point 1 on this board should have approximately 5 volts, and it does. By following the schematic further through, we can see that test point 3 should have approximately 5 volts, and it does. Going through test point 3, we can go up to test point 4, and we find that test point 4, which should have 5 volts, is potentially a 0 volts, which is ground. Going back between test point 3 and test point 4, we find a capacitor that goes directly to ground, and we can measure the top of that cap, and we find that it is also 0 volts, which tells us that it is shorted to ground. In my job as a technician, it is very important that I understand the properties of voltage pushing current or electrical charge through a circuit. In this example that we have just seen, it is evident that I would not have been able to fix the circuit without knowing these properties.
Because voltage is a prime mover and acts like force, you can always add more when you need it. For example, each battery in this flashlight only produces 1.5 volts. But the bulb needs 4.5 volts to shine brightly. So, 1.5 added 3 times is enough voltage to do the job. When batteries are recharged, more voltage is being added. Electrical systems are an important part of our lives, but even though we move it around the country and use it in so many ways, no one has ever seen electricity. Electrons are simply too small to be seen. Still, anyone who works with an electrical system must understand where the source is, know how to follow the flow of electricity using a circuit diagram, and how to find the voltage at any point along the circuit. In the same way that force determines how an object moves in a mechanical system, voltage determines how a charge will move in an electrical system. Without voltage, electricity just doesn't move. In fact, it doesn't even exist.
Hey!
When we think of moving heat, we usually think of something like this. Heat can be moved into an object, but it can also be moved out. This fish processing plant removes heat from the fish by using temperature difference as force in a thermal system. Thermal systems move heat from place to place in the same way that fluid systems move liquids and electrical systems move charges. What does heat really mean? When we talk of something being hot or cold, we're really talking about the activities of the very atoms and molecules of which the substance is made. When something gets hot, its molecules move faster. They have more energy. It's something like this popcorn. The kernels are like molecules that start out with low energy, but when they start popping and dancing around inside the pot, they have more energy, like the molecules of a hot object. Thermal systems usually add heat, but Mike Ivor's job is a little unusual because his system takes heat away.
This thermometer says 100 degrees Fahrenheit, but it's below zero. It's about 60 degrees in this room, so there's 160 degrees difference in temperature. We're trying to freeze fish very quickly in this tunnel, about 8 minutes. This is liquid carbon dioxide. If you tried to do this in a home freezer, it would take an hour. Here it will only take a few seconds. What we've done is pulled the heat from this piece of fish. The reason that works is because of the large temperature difference. I have to know about how temperature difference moves heat in order to maintain this machine.
Heat will move from warm areas to cold, from areas of high energy to low, and it's moved by temperature difference. Temperature difference is what acts like a force to move heat in a thermal system. Even popcorn kernels will move from areas of high energy to low if they're able. This is how heat moves from warm areas to cold in a thermal system. Temperature difference is symbolized by delta T. It's found by simply subtracting one temperature from the other. Mike's room is 60 degrees Fahrenheit above zero. That's 15 degrees Celsius. But the freezer is 100 degrees below zero. That's minus 73 degrees Celsius. So delta T in this system is 160 degrees Fahrenheit. The larger delta T becomes, the faster the heat will move. That's why the fish freezes so fast. Heat flows out through the walls of a house in winter because of temperature difference. If the temperature inside is 70 degrees Fahrenheit and the temperature outside is 30 degrees Fahrenheit, what's delta T? Can you find delta T in summer when the temperature inside is 70 degrees and it's 110 degrees Fahrenheit outside? Delta T is the same, but the heat moves in the opposite direction. Knowing the temperature difference between inside and outside will determine how much insulation is needed to reduce the flow of heat. The principle of moving heat from one place to another is the same in the freezer as it is for blast furnaces, power plants, and even rocket engines. In all cases, technicians have to find areas of high temperature and low and understand how temperature difference acts like a force
Frozen.
to move heat.
Too frozen.
In this unit on force, we have seen many different energy systems in action. They all have something in common. Each system has a prime mover and something being moved from one place to another. In mechanical systems, force is the prime mover that moves objects around. In fluid systems, pressure acts like force to move liquids and gases through tubes. Electricity is moved through circuits by voltage in electrical systems. And heat is moved from warm areas to cold by temperature difference in thermal systems. Force, pressure, voltage, and temperature difference are all prime movers, while the object, the fluid, the charge, and the heat are the things that are being moved. Since all these prime movers move things from place to place, they all are or act like force. Listen again to the technicians. Even though they all work in different systems, they all talk about a push or a pull.
As an electrician who maintains the equipment on the crane, I have to understand force and the pulling of the force so I can set up the parameters to limit the amount of pull that the crane can exert.
In the fluid system,
It's very important for me in my job to understand how pressure moves liquid as a force to a lower pressure. It's like an electrician would have to know how voltage moves a charge. And if we don't know that, I cannot properly do my job, because pressure differential is probably the main ingredient in us producing our product. And if we don't understand that very well, it causes a lot of problems.
In the electrical system,
In my job as a technician, it is very important that I understand the properties of voltage pushing current or electrical charge through a circuit. In this example that we have just seen, it is evident that I would not have been able to fix the circuit without knowing these properties.
and in the thermal system.
What we've done is pulled the heat from this piece of fish. The reason that works is because of the large temperature difference. I have to know about how temperature difference moves heat in order to maintain this machine.
Each system had more than one prime mover in action at the same time, so the technicians had to identify where each prime mover was acting, add those that act in the same direction, subtract those that oppose, and find the total. In the mechanical system, the total is net force. In the fluid system, it's total pressure. Electrical systems have total voltage, and thermal systems use temperature difference. Technology is not getting any simpler. Even the everyday car has become an incredible arrangement of different systems. There's the mechanical moving parts, there's fluids being pushed around by pressure, voltage is pushing electricity through circuits and even computers, and heat is being taken away from the engine by temperature control. It can all seem quite confusing. But complicated technology can become a little easier to unravel, and therefore easier to work with if you understand force and how it causes things to move. Or not move. But remember, when you do isolate one of the systems and solve a problem in it, there may still be another problem in another system down the road. This program was produced at the facilities of Telemation Productions and is part of Principles of Technology, a project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development. Together, serving education.